Okay, perfect. So it's a great pleasure to have Russell Avdek from Orsay, but who is joining the chat from Nantes today. Who'll be telling about contact homology, Gromov-Witten, and the geography of tight convex hypersurfaces. Take it away, Russell.
Yeah, thank you so much. Thanks so much for the invitation and the introduction. Yeah, so as mentioned, the title for today's talk is Contact Homology, Gromov-Witten, and Geography of Tight Convex Hypersurfaces. And so what are we going to talk about today? So the goal is to understand convex hypersurfaces in high dimensions. And so before getting into what they are, so broadly, they're objects which are central to contact topology. And there's currently a hot research topic, and that there's sort of a lot of activity going on, and we're just figuring out the basics. We currently know close to nothing in high dimensions. And that's a result of us having very few available tools and not understanding a lot of examples. And so getting a little bit more into the specifics, today I'm going to talk about the theorem today is going to say that characteristic classes don't obstruct tightness of convex surfaces in 4+1 dimensions. And if you don't know what that means, it's okay, I'll explain shortly. But the main theorem is going to contrast with the Thurston-Benneken bound, which is a well-known thing which happens in 2+1 dimensions. And this is going to fit into a sort of very imprecisely stated conjectural picture, which is that there's conjecturally there's always going to be a lot of tight contact structures in high dimensions and few obstructions to them existing. Getting into the specifics, what I'm going to do today, so I'm going to start off reviewing what's known and what's not about these convex hypersurfaces, and then I'll state my main theorem and prove it around the geography of convex hypersurfaces dimension 4. And so we have our big application. The talk is also an excuse to talk about some computational techniques, first for contact homology of these convex hypersurfaces, and for constructing these convex hypersurfaces. And so that's what we're going to do, and this is going to cover some work which is not in the archive yet, but it's going to cover an upcoming sequel for a paper I put out a few months ago called An Algebraic Generalization of Giroux's Criterion. And so, to get things started, I'll do a crash course in contact topology, meaning just setting some notation and sort of setting what my perspective is. So we're going to be dealing with contact manifolds dimension 2n+1. Everybody are presumably those Liouville manifolds, which we view as the things which give rise to contact manifolds is contact manifolds or boundary of Liouville manifolds. And the most interesting examples of Liouville manifolds are those which are Weinstein, meaning those which can be built out of handle attachments whose index is at most half the dimension of the Liouville manifold W. Our main examples are algebraic varieties. So we take an algebraic variety in Cn, and we intersect it with a very big ball, and this gives us something which is compact and made out of these handles. That's our first example. Our second example are we take a closed manifold and we take its disk cotangent bundle. This is going to be a Weinstein manifold, and studying these objects, this is the setup for mathematically doing Hamiltonian mechanics on the base. And so we think of Liouville manifolds and Weinstein manifolds as their own entities and also as fillings of contact manifolds. And so that's sort of what Liouville manifolds are about. For contact manifolds, we think of them as falling into two distinct classes, being either tight or over twisted. Fillability of contact manifolds, meaning that they're the boundaries of a symplectic manifold, implies their tightness. And the main theorem regarding over-twisted contact structures, aside from obstruction to fillability, is that for each formal homotopy class of almost contact structure, on a smooth manifold, there's a unique over-twisted contact structure in that homotopy class. So they're just like homotopy theoretical objects. And then we know that there's, by Cassius-Murphy process, there's many ways of describing over-twistedness. And some of the, sort of from my perspective, some of the important questions I'm interested in addressing in my research are, or, you know, for contact topology in general, is if we have a homotopy class of a plane field, or an almost contact structure on a smooth M, is there a tight contact structure in that homotopy class? And then if we're given a contact manifold via some kind of description, we want to know, is it tight or fillable? Studied in the three-dimensional case, typically using convex surfaces. So what we want to do is we want to understand convex hypersurfaces in higher dimensions, and then hopefully use them to help address these kind of questions. So what is a convex hypersurface? So I take an even dimensional 2n manifold inside of a 2n plus 1 contact manifold, and it's convex if it has a neighborhood of the form interval times hypersurface S, along which, and I'm going to use the variable tau for this interval. So I have this neighborhood along which the contact hyperplane field is tau invariant. And so whenever we have this situation, we can assume that we can describe the contact structure as a kernel of a contact one form, written like fd tau plus beta for a function f on the hypersurface and a one form on it. And when we do this, it decomposes the hypersurface into a negative region, which I'll always color blue, a dividing set, which will be purple, and a positive region, which will always be red. And these inherit geometric structures from the contact structure. On the positive and negative regions, we get Liouville structures, and in the dividing set, we get a contact structure. So our perspective for these objects is that a convex hypersurface is Leo with their boundaries identified, having the same boundary gamma and having these boundaries identified. So this means when we have, for example, in the n=1 case, we're dealing with Riemann surfaces. The positive and negative regions are just compact oriented surface with boundary. So the whole data is just determined by this, by a closed oriented surface with a null homologous multi-curve in it. We can take the multi-curve as being the boundary of the positive region. So that's sort of, you know, we sort of know what all of the convex hypersurfaces look like in dimension 2+1. And, you know, so we think we know less about the higher dimensional cases, but, you know, because if we work in the 4+1 dimensional case, we actually know a lot about fillings of contact 3 manifolds, for example, written from Kirby calculus and mapping class group perspective. So this provides us tons of examples of 4+1 dimensional convex hypersurfaces, because we know lots of fillings of contact 3 manifolds. Okay, and now getting into the main theorems, you know, how do these sort of behave in nature? The first is due to Giroux in the 3-dimensional case and Honda Huang in the higher dimensional case. The theorem says that a C0 generic oriented hypersurface in a contact manifold is convex. And moreover, in this C0 generic setup, the positive and negative regions are not only Liouville manifolds, but Weinstein manifolds. So this is very strong. And then in the low dimensional case, we know exactly when convex hypersurfaces have tight neighborhoods according to this theorem called Giroux's criterion. And it says that when we have a 2-dimensional convex surface, that it's tight if and only if the following criterion is met. If it's a sphere, we require that the dividing set is connected. So it just means it's a sphere with just an equator dividing set. And in all other cases, the neighborhood is tight if and only if the positive and negative regions have no disk components. So this is really elegant. It's like really nice to state. It's in terms of curves on surfaces, and it's you know, easy to use and easy to state. concept of it is what we call the Thurston-Bannikin bound, which is using a different technique. And it says that whenever we have a convex surface in a contact-free manifold, which is tight, then the Euler class or the Euler number of the contact structure has to be less. Its absolute value has less than or equal to the absolute value of the Euler characteristic of the surface. And so this has like huge consequences. It's a kind of Thom conjecture type thing for tight contact structures. So for example, as a consequence of this, as a Bannikin bound, only finitely many H2 classes or second cohomology classes can be realized as the first Chern classes of tight contact structures on a fixed M. So this means so I guess this fits into this sort of this picture of in dimension 3 tight contact structures being pretty rare. And there's a lot written about this. For example, there's like a unique tight contact structure on S3. These results of Colin, Giroux, Honda talk about other limitations on which homotopy classes support tight contact structures. And we're interested in maybe talking about tightness in high dimensions is a little bit too difficult. We can ask, is there a higher dimensional generalization of Giroux's criterion? Maybe an easier question would be, is there a higher dimensional generalization of the Thurston-Bannikin bound? And today, that's going to be the main question we're going to address. So we say, the basic question is there some higher dimensional generalization of the Thurston-Bannikin bound? So to look for higher dimensional generalizations, the inequality concerns Euler class of a contact structure and Euler characteristic of a convex hypersurface. If we go up in dimension, we're going to look at Chern numbers of the contact hyperplane fields and invariance of the hypersurface itself. So the natural thing to do is to say, we'll look at the 4-dimensional case, the Euler characteristic and signature of the surface of the hypersurface, as well as these Chern numbers. So it's just C1 squared and C2, which is just the Euler class. And it's a basic, or maybe not too difficult exercise in characteristic classes that these invariants satisfy the following relations. The first is that the Euler characteristic of the hypersurface has to agree with the Euler number of the Euler number of the contact structure mod 2. The hint is that they're both just the Stiefel-Whitney number. And then we have that the Euler class plus the signature has to be 0 mod 4. And this comes from, you can just look at the additive generators of the 4-dimensional complex cobordism group. It's CP1 times CP1 and CP2. They both satisfy that. And then we have a third relation, which says that the C1 squared is determined by the signature and Euler number. This is just a Hirzebruch signature formula type of thing. Anyway, so we have these 4 numbers and we have these relations. And the theorem that I want to prove today is that for any 4 numbers, 4 integers satisfying these relations, I can find a closed connected dimension 4 convex hypersurface with a tight neighborhood whose invariants are those invariants, those numbers. And so this means in particular, when we look at just the Euler characteristic and signature, this sort of what we would expect from the Thurston, there's no generalization of this Thurston-Bannikin inequality just comparing those invariants. So we can take this difference, absolute value of the Euler characteristic minus Euler number, and this takes on all values in 2z. And so that's a lot of numbers. What I'm saying, and at that sort of high level, is that there's no characteristic class obstruction to tightness in dimension 4+1, at least for neighborhoods of these convex hypersurfaces. And this contrasts with this low dimensional case. So that's what we want to prove today. And the outline of the proof is going to be one, I'm going to describe a method for constructing interesting convex hypersurfaces in any dimension, but it's going to be especially easy to use in this 4+1 dimensional case. Then for the second part, I'm going to use contact homology to show that a lot of convex hypersurfaces are tight. And this is going to be building on top of some of the previous results. And then, so I'm going to be able to prove that some convex hypersurfaces are tight using contact homology. Then I'm going to modify them using a bunch of handle attachments so that I can get any Euler characteristic and Euler class and signature that I want. And then I'm going to show that these surgeries which I'm performing don't modify the non-zero contact homology condition. And so that's going to be the whole the strategy for constructing these things. And along the way, I'm going to talk about how we can compute contact homology for these objects, and we'll carry out some what I think are pretty fun Gromov-Witten counts along the way to carry out those computations. Okay. Any questions before I move on? I guess people can post in the chat. Okay. So the first thing I'm going to do is I'm going to have a means of constructing interesting convex hypersurfaces. And the definition is going to be based on this familiar Gompf fiber sum construction. So before I get into what the construction is, what the input objects are closed integral symplectic manifolds equipped with Donaldson divisors. So if I have X omega is my closed symplectic manifold, D is my divisor, which means that its point create dual to the symplectic form. Then the complement of this divisor is going to be Liouville, and in practice, we're always going to take these things to be like cut out by line bundle, like holomorphic line bundles on Kähler manifolds. So everything is going to be algebraic. And in that case, then we're going to end up with the complements being affine varieties, which are Weinstein, so they're really nice manifolds. And when we take the normal bundle to the divisor, its first Chern number is just the symplectic form itself. And the boundary of this tubular neighborhood is going to be something which I'm going to call gamma, and this ends up being a pre-quantization S1 bundle over the divisor. Okay, so now I know sort of what happens if I have a single divisor in a single closed symplectic manifold. To carry out my construction, what I'm going to do is I'm going to take what I call a divisor pair. So I take two closed symplectic manifolds with divisors in them, and this thing phi. And so the X plus minus omega plus minus D plus minus are these closed symplectic manifolds divisors, and then I have a symplectomorphism between the divisors. Whenever I have such a collection of data, I can build a convex hypersurface by taking the complements of the divisors on both sides and identifying their boundaries by lifting this symplectomorphism of the divisors, contactomorphism of the associated S1 bundles. And this is going to give me lots of interesting convex hypersurfaces, and they're going to be pretty easy to find, at least in low dimensions. So as I mentioned, this is basically, it's a ripoff of the Gompf fiber sum operation. In the Gompf fiber sum operation, you want normal bundles to be anti-holomorphically identified. Here, I want them to be holomorphically identified. And so to see that it's not completely coming out of thin air, it's pretty easy to see that whenever I have a convex surface, this of two dimensions, it comes from this construction, meaning, well, I can take two possibly disconnected closed Riemann surfaces. I have a bunch of points in them. That's what a divisor is in that dimension. I remove the points and then I glue what's left over together. Every convex surface of dimension 2 can be obtained in that way. So yeah, so these things are everywhere in 2 dimensions, and it's maybe not that interesting to construct them in that fashion, but if we're working in real dimension 4, these are very easy to construct, and they give lots of fun examples. Specifically because a neighborhood of a divisor in a 4 manifold is just determined by its self-intersection number and its Euler characteristic. So this means we can take like lots of complex surfaces, just write down some polynomial equation. This is how algebraic geometry works, and then we get these fun divisors, and they exist in abundance, and it's easy to sort of compute with them. So I'm going to talk about 2 classes of two sequences of such examples. The first example is going to be I'm going to look at my closed symplectic manifolds being P2 and P1 times P1. I'm going to take from my negative side, divisor of degree 2k in P2, and on the positive side, a divisor of degree 2kk in P1 times P1. These form divisor pairs, as you can see from the basic Euler characteristic and self-intersection number calculations. And so these are really nice, and they're sort of topologically pretty non-trivial objects. And they actually come from some pretty familiar constructions. So these come from pencils, algebraic pencils on some pretty well-studied complex surfaces. And so these things come equipped with the complements of the divisors have come equipped with some natural Lefschetz vibrations. If we in particular look at this k is equal to 1 case, we end up getting the distinct fillings of the canonical contact structure on L41, which is studied by McDuff. And if we look at the total monodromies of these Lefschetz vibrations, in this k is equal to 1 case, then on the one side we're going to get so the fibers of these Lefschetz vibrations are always 4 punctured spheres. On one side it was observed that we have 1/2 of the Lefschetz, 1/2 of the lantern relation, as you can see on the left here, and coming from this pencil on P2. And the same analysis tells you that if you look at the associated pencil on P1 times P1, it gives you the other half of lantern relation. So these things are just indexed by k, and we have a whole family of such generalized lantern relations. So that's one family of examples, and we have another family of examples. This is going to be necessary, but you can see that these things are, it's really easy to find lots of examples of these divisor pairs. For our second class of examples, I'm going to index them by an integer L, or a positive integer L. And I can just take in a genus 2 surface times a genus 2 surface. I can take a divisor of degree 2L2L. And I can in from my positive side, I can take a divisor of degree 4LL in a genus 2 surface times a genus 1 surface. Again, these self-intersection numbers and Euler characteristics agree. And so this gives me another family of another infinite family of convex hypersurfaces. And these are going to be, so our goal is to like construct some convex hypersurfaces with some specific signatures, Euler characteristics, Euler numbers. These are going to be our main building blocks. And so what I'm going to want to do to check the tightness to establish that some of these convex hypersurfaces are tight is I'm going to be using contact homology, which is an SFT type invariant of contact manifolds. And so And so in order to use it, I'm gonna discuss some algebraic machinery to actually compute it for convex hypersurfaces. But so I'm gonna do a really quick review. The first so just to say like what it is and what are we doing with it. The reason it's used to study tightness is we have this theorem of Bourgeois, Van Coort, Eliashberg, and Yau, which says that if we have a contact manifold, if its contact homology is non-zero, this means the contact manifold is tight, which is the geometric property we're interested in. And what is this thing? It's the homology of a differential graded algebra. On the chain level, we have an algebra generated by the Q vector space of reorbits. So it's just this symmetric tensor algebra equipped with a Leibniz rule for our differential. And the differential itself counts holomorphic curves in the symplectization of the contact manifolds, specifically having one positive puncture and any number of negative punctures, and G is 0. And this gives us a differential which breaks up into a number of terms. Each of the terms counts holomorphic curves with some fixed number of output punctures. So this is our algebra. We're interested in its homology. And an interesting property of it is that if we have a Liouville filling of a contact manifold, this gives me an augmentation of the chain level algebra, which is just a DGA map to the rational numbers equipped with a trivial differential. So that's the sort of high level on what it does. And we're interested in situations in which we have these convex hypersurfaces. And so we want to compute, our ultimate goal is to compute the contact homology of the neighborhoods of these things to establish their tightness. And you will recall that our perspective is that a convex hypersurface is two Liouville manifolds with their boundaries identified. So in such a situation, I have two augmentations of the contact homology algebra of the dividing set. And so these augmentations I can write down as epsilon plus and epsilon minus. And using the pair of two augmentations, I can define a homology theory and an augmentation of that homology. So the homology theory goes that I take the vector space of orbits, I do some grading shift to it, and I define a bilinearized differential. The bilinearized differential says I take all the original differential terms with at least one output, and I cap off the all but one negative end of the outputs using the augmentations from either the positive region or the negative region in any possible order. This gives me a differential on this vector space of orbits. And then I also have a map from this vector space of orbits to the rational numbers, which just says take the difference of the augmentations. It's non-trivial to check, but it's true that these give you commutative versions of objects which were familiar from Legendrian contact homology theory, which is due to Bourgeois and Train. So first, just taking this differential, which has one output, the homology of this is going to give me something called bilinearized contact homology, which is analogous to the familiar linearized or bilinearized, or the linearized contact homology that we know for contact homology, or the bilinearized contact homology that we're familiar with from Legendrian contact homology. So we have this structure, and then associated to it, we also have this fundamental class structure, which says that I just take this object, the induced morphism on the homology, the bilinearized homology to the ground field. Homological structures. From this, I also get a chain level thing, a new chain level object, which is the algebra coming from the vector space of orbits, now with a shift in grading, and then a differential, which is just this fundamental class plus the bilinearized differential. So the same relations that say d1 squared is equal to 0, d0 d1 is equal to 0. The relations that say that that's a homology theory and that's an induced map from the homology theory to the ground field say that this new object is a DGA, just as the d squared is equal to 0. And this object I'm going to call the bilinearized DGA. Okay, so maybe it's a lot of vocabulary right there, but we'll see why we care about it right now. So again, we have a convex hypersurface. We think about it as positive region and negative region glued on their boundary. This gives rise to a pair of augmentations and all this homological algebra objects which I just described. And the theorem is that you can make choices in terms of geometric data so that the contact homology algebra of the neighborhood of the dividing set is on the chain level equal to this bilinearized contact homology associated to the pairs of augmentations. Okay, that sounds like that gives us a chain level description of something. Okay, what do we do with that? We care about homology. If you do a little bit of algebra, then you can see that the contact homology of the neighborhood of the convex hypersurface is non-zero if and only if this fundamental class is 0 on the bilinearized contact homology. Okay, so again, it's like, bear with me. It sounds like it's maybe like a lot of vocabulary items. And we also we sort of want to understand what's going on with the computations of these augmentations in practice, because they might be difficult to compute. But at least for some classes of examples, it's actually pretty easy to see what's going on here. Specifically, when we have these convex hypersurfaces determined by divisor pairs, we have a lot of friendly index formulas, which will often tell us that the augmentations are just 0 for index reasons. And in such situations, that'll just tell us there's no augmentations. This fundamental class has to be 0. The contact homology is 0, and therefore the convex hypersurface is tight. And in some situations, we can't say that there's no holomorphic curves for index reasons. But then we can actually just do the counting of the holomorphic planes of these augmentations using relative Gromov-Witten, using relative Gromov-Witten theory. And relative Gromov-Witten theory is often really, really difficult, but then also sometimes it's really easy and fun to compute because the computations boil down to some classical enumerative geometry. Okay, so we're going to talk about now, so I have these examples which I'm going to use to prove my main theorem. They're built from this divisor pair construction. I'm going to talk about how we can compute augmentations of the positive and negative regions of those hypersurfaces, which are complements of divisors in what are going to be Kähler surfaces. So to compute these augmentations, so to compute this contact homology, I need to compute these augmentation planes and these divisor complements. And the geometric setup for doing so is as follows. So when I have this a neighborhood of the divisor, the complement is going to be a Morse-Bott contact form, where it's a circle bundle over the divisor, and the read vector field is just doing fiber-wise rotation of the S1 fibers. So it's a Morse-Bott situation. We have to break the symmetry, I just talked about in like a Frederick-Bourgeois thesis. And so to do that, we can put a Morse function on the divisor. And this is going to give us a much friendlier read vector field whose closed orbits are just indexed by the critical points of the Morse function together with some what the covering multiplicity is. And the closed reef orbits are going to be the S1 fibers of this fiber critical points with some specified covering multiplicity. And we have, when we do this nice geometric setup, we have really friendly formulas for the indices involved. The Conley's inner index and Morse, and contact homology gratings just boil down to computing the Morse indices. And so that's sort of our basic setup. And now I want to upgrade this a little bit. So what I can do is I'm interested in computing the indices of holomorphic planes asymptotic to these orbits in this divisor complement. So if I'm given such a plane, what I can do is I can just add the point at infinity back in, the point over which so it's going to be asymptotic to some multiple cover of a circle fiber of this neighborhood, boundary of this neighborhood. So I just fill in the point to which it's asymptotic, and this gives me a map from a closed CP1 into now the closed divisor. And it's passing through the divisor at exactly one point at infinity. And so using these completing planes to spheres, I can relate index formula and these covering multiplicity calculations to intersection formulas and Gromov-Witten index. Covering multiplicities of the positive ends of these planes, as well as their Fredholm indices using these two friendly formulas. And so you can see that everything involved here. There's like some intersection CP1 and some Turing class data and some Morse index data. So when we're thinking of things like intersection numbers and Turing classes, these things are extraordinarily easy to compute with when we're talking about divisors in complex algebraic varieties, especially if they're really easy to describe varieties like CP1 times CP1 or CP2. So the takeaway is I have these really friendly index formulas. And these formulas tell us, we can often just look at the index formulas and see that there's no holomorphic planes that could possibly contribute to these augmentations. And so that's actually going to be enough to prove the main theorem we want to prove today. But I'll talk a little bit about, you can actually, I think it's sort of interesting when you do want to count these planes. So in a simplified version of some of Diogo-Lisi's work, says that if we have such a setup, we have a Morse function on this divisor which has exactly one maximum and then one minimum, then we can count these holomorphic planes as follows. So assuming that all the moduli spaces involved are transversely cut out, then there's orbits. We're interested in the orbits going to this multiple covers of this maximum Morse maximum orbit and this Morse minimum orbit. The count of holomorphic planes asymptotic to the Morse minimum orbit is the Gromov-Witten count of holomorphic spheres touching the divisor exactly once at specifically this Morse minimum point. And if we want to count the number of holomorphic planes asymptotic to this multiple covers of this this Morse maximum critical point, this is the Gromov-Witten count of holomorphic spheres passing through the divisor exactly once, with no point on exactly where that point is, no constraints. And in the goes multiplicity of the orbit is going to correspond to the order of contact of this CP1 with the divisor. So it might if it intersects transversely, cover. If it intersects it with some degeneracy, that's going to have simplified setup where n is equal to 2, so everything is particularly friendly. Again, getting back to like, what do we want to apply this to? We have these two families of examples of convex hypersurfaces. The first was we have this degree 2k divisor in P2, and we also consider a degree 2kk divisor in P1 times P1. This gives us one series of convex hypersurfaces indexed by a value k. We have another series indexed by L, which is degree 2L divisor times sigma 2, and degree 4L divisors in sigma 2 times sigma 1. And so the computation is, for these examples, the contact homologies of the first series, the P2 and P1 times P1 series, they're non-zero if and only if the k is bigger than or equal to 3. And for the other series involving genus bigger than 0 surfaces, the contact homologies are always non-zero. So in this second case, remember we're relating computations of augmentations to holomorphic spheres. There's just no holomorphic spheres that count because we're dealing with products of g bigger than 0 Riemann surfaces. So this sort of for the second class of examples, the computations are trivial. And I want to prove that these contact homologies are going to be non-zero for this more interesting class of examples, where it's complements of divisors in P2 and P1 times P1. And we're only going to need some of these to prove the main geography theorem, but I think the computations are too fun to skip in the k is equal to 1 and 2 cases, so I'm going to carry them out. So let's work out this computation. So the claim is that when I have this a quadric in P2, and then I take a degree 2, 1, that the augmentation counts are going to be different on the different sides. And if you recall, this is the example which is particularly interesting because it corresponds to a lantern relation. So what I'm going to do is I just need to show that the augmentations are different for a single orbit, which is going to be closed under the contact homology differential. So what I can do is I can look at the orbit corresponding to the Morse minimum on my divisor, which is just a P1. And I want to count the augmentation planes sitting in these two Weinstein or algebraic manifolds asymptotic to this orbit. And so using this index formula, I can see that there's nothing to count on the negative side, which is the complement of the quadric in P2. And if I do a little bit of arithmetic with these formulas, I see that on the positive side, so I'm in P1 times P1. All of the holomorphic planes, if I close them to spheres, have to be in the class P1 times points. And so, the thing that in order to compute this augmentation, I'm counting the number of holomorphic spheres in P1 times P1 in class P1 times point, which pass through a specific point. This is classically known to just be, there's exactly one sphere through this point. So this tells me that backtracking through all this algebra, the differential of this orbit in this contact homology algebra is equal to 1. So this tells me that the unit in the algebra is exact, the algebra is dead. And so this tells us contact homology is 0. So that's one computation, and you see it just comes from some I guess the thing which I'm interested in marketing to people is that you can do these really interesting contact homology computations just doing some like enumerative geometry basic stuff. Here's like a more interesting calculation, and is k is equal to 2k's. So to state what we're trying to figure out, we have this convex hypersurface determined by whose negative region now is the complement of a degree 4 curve in P2, and whose positive region is the complement of a degree 4-2 curve in P1 times P1. And in this case, the divisor is a genus 3 surface. And in this case, remember we have to have the we want to understand the contact homology differential on this pre-quantization space, and then these augmentation planes. The contact homology differential on gamma, which is this pre-quantization space, is just 0 because it's known that this just counts some Morse flow lines, and there's counts of Morse flow lines on genus 3 Riemann surfaces are 0. So our differential only counts these augmentation planes, and we're going to show that this DGA is 0 by studying a particular orbit, which is the twofold cover of the Morse maximum critical point. So before we just did the Morse minimum critical point, the one-fold cover. Now we're going to look at the twofold cover of this maximum. So again, we run our arithmetic. We see that there's no index 0 planes asymptotic to this orbit on the U minus side in P2 complement of this divisor. And then we want to look at now how many holomorphic planes are planes are asymptotic to this thing in the complement of this 4-2 divisor in P1 times P1. So again, we run this arithmetic engine, and it tells us that the only that in order to count these planes, it's equivalent to counting holomorphic spheres of homology class P1 times point in degree touching this divisor of degree 4-2 with order of contact 2. And so this is a more okay. Anyway, so now we're in the thick of things in the middle of this interesting computation. So we're counting these augmentation planes asymptotic to twofold covers of this Morse maximum orbit. And so we know using this Diogo-Lisi technology is this equivalent to counting holomorphic spheres in P1 times P1 in this class P1 times point, passing through this divisor with order of contact. I think someone. Anyway, so okay, so let's carry. So let's carry out this Gromov-Witten count. If we have a generic line of class 1,0 passing through this divisor, it's going to do it transversely through 2 points. And there's going to be special lines at which those 2 points converge, and the line is going to pass through the divisor once with multiplicity 2. So counting those special lines, this occurs exactly at the critical points of a map, which is I project P1 times P1 onto the second P1 factor. I take the restriction of this map to the divisor, and it's a map now from a genus 3 surface to a sphere. The critical points of these maps are going to correspond exactly to these lines with order of contact 2. So in order to count these lines, I can just count the number of critical points of this ramified covering of the genus 3 surface over a 2 sphere. Riemann-Horvitz tells me that there's exactly 8 such critical points. And so now I know that this is the number of augmentation planes that I'm counting is 8. So rolling back and combining all this, combining everything on this slide, we have that this the contact homology differential of this orbit is this count of special lines, which by Riemann Horowitz is 8. And since I'm working over the rational numbers, I have the differential of an element is a unit in the algebra, and so it kills the entire algebra, and the contact homology is 0. So this was again an example where you can carry out some fun computations using basic arithmetic and get some interesting contact topological information out of it. So those are the remember we had this series of convex hypersurfaces indexed by this integer k. The theorem was that for k is equal to 1 and 2, the contact homology vanishes. For k bigger than or equal to 3, it's non-vanishing. And so to carry out these remaining cases, we just do these index computations, and it shows there's nothing to compute. So there's no augmentations, and we know that the contact homology of these neighborhoods of these convex hypersurfaces are always non-zero. So let's just recap. We have this first family determined by divisors of P2 and P1 times P1. Their signatures are -1, and their Euler characteristics are 1, and this contact homology is non-zero whenever this indexing k is bigger than or equal to 3. And we have this second family, which is divisors of products and some other Riemann surfaces. In this case, my signature is always 0. My Euler number of the contact hyperplane field is -4, and the contact homologies are always not 0. And I remember, just to review, what are we trying to ultimately do? We have these restrictions imposed on our characteristic numbers, and we want to prove that for all possible characteristic numbers subject to those restrictions, we can find connected 4-dimensional tight convex hypersurfaces with those invariants. And so we look at our building blocks. One of them has signature -1, and the other one has Euler number -4. So what I can do is just to get the signature and Euler number correct, I can take a bunch of copies of the K series convex hypersurfaces with K bigger than or equal to 3. This gives me a disjoint union. This gives me a disconnected convex hypersurface with signature any integer that I want. Right, and now I know that this gives me the correct signature. Now I want to get this Euler number correct. And I know that the Euler number plus the signature has to be equal to 0 mod 4. This one, the second collection of convex hypersurfaces, they have Euler number -4. So I have the disjoint union to get the signature correct. I can add disjoint unions of the second type of objects with the orientation corrected as necessary to get both the signature and the Euler number correct. And so now I have this disjoint union of convex hypersurfaces. The result is tight because it's a disjoint union of tight things, and it has disjoint union as non-zero contact homology because it's the contact homology, the disjoint union is just the tensor algebra of the contact homologies of the connected pieces. And now we have everything except for the Euler characteristic. So remember, I want to get these 4 numbers to look like whatever we want. So far, we have the Euler number, the signature, and the C1 squared doesn't matter because it's given to us determined by the other invariants. So now I just want to make the Euler characteristic of a convex hypersurface whatever I want, and I'm going to do that by attaching some handles to this disjoint union. So So as I said, I'm going to add some handles to make this disjoint union connected, and then make the Euler characteristic whatever I want. And then I'm going to show that this handle addition doesn't change the non-vanishing of the contact homology. Okay, so the thing we're going to do is we're going to attach what are called contact handles. And so the way that we these are sort of pretty classical, or I mean, these are going back to being thought about in like papers of Giroux, in the 90s. So we're going to attach these contact handles to the boundary of a neighborhood of our convex hypersurface, and sort of what the picture looks like in general is that if I take a neighborhood of a convex hypersurface, and if I look at the dividing set, which is in one of the boundary components, it's going to look like a contactization of a symplectization of the dividing set. So symplectization means I extend it in one direction by an interval, giving me something like e to the s times a contact form on the dividing set itself. And then I extend this in another direction along which the contact structure is T invariant. So what this means, I guess in practice, is that if you look at a convex hypersurface from the outside, it's sort of it looks like a hockey puck with some corners, and where the top is the positive region and the bottom is the negative region. And to make everything smooth, you just round the corners. So if we think about it from this sort of point of view where there's corners, well, then it's pretty easy to figure out how these things can be modified. We can just take a Weinstein handle times an interval, and we can attach it to the boundary. And this is called, and then, so you sort of take a smooth thing, add corners, attach handles, do corner rounding. And this is called contact handle attachment. Whenever we do this, the convex boundary is changed so that the negative region becomes, the new negative region is the old negative region union this Weinstein handle. The positive region is the old positive region union this Weinstein handle. And consequently, the Euler characteristic jumps up 2 times the index of the handle. And signature and Euler number, they're not going to change under this type of operation because they're homological invariants. And not only that, we have some results of Colangagini, Honda, and Hutchings, which says we can do this contact handle attachment to the boundary of any contact manifold with convex boundary. And when we do, it doesn't change the contact homology of the manifold. And this maybe isn't so difficult to see, or at least to believe, being that you can see that there's all the reorbits passing through the handle are going straight up, so we're not creating any new closed reorbits. Okay, so this is the technique we're going to do. And we already constructed a disconnected convex hypersurface with desired signature and Euler number, and we just to figure out the Euler characteristic and connectedness. So we can add these contact 1 handles to the boundary of a neighborhood of the convex hypersurface S, which is our disconnected hypersurface. We add 1 handles to make it connected. And then we can add 1 and 2 handles however we want in order to get the Euler characteristic to be whatever we want on the new on the boundary component of on this contact manifold obtained by taking the neighborhood of the original convex hypersurface, adding handles. Now we have another convex hypersurface on the end. And so now the inclusion of the original convex hypersurface into this 5 manifold, we know from the theorem stated on the previous slide, induces an isomorphism on this contact homology. So in particular, it's non-zero. And then we also say, now this new boundary component, this has the convex hypersurface we want to prove is tight. We have a morphism from the contact homology of the neighborhood of that convex hypersurface into this 5 manifold, which has non-zero contact homology. And this inclusion morphism is a unit algebra morphism. So in particular, you can't have 0 mapping to something non-zero. So this tells me that the neighborhood of the new convex hypersurface is non-zero. And so consequently, that wraps up the whole theorem, and now we're done. So we proved that we have, whenever we have these this collection of 4 integers satisfying these necessary relations coming from characters to class computations, we have a tight, a 4-dimensional convex hypersurface with tight neighborhood whose invariants are given by the numbers. In some closing remarks, this is our theorem, and so something I talked about at the very beginning was, how is low-dimensional contact topology different than high-dimensional contact topology? There's already been some, the main theorem is sort of saying that there's no such thing as a Thurston-Benneken bound in dimension 5. There's been something like this is perhaps expected because there's been some previous results due to Mori about the non-convex hypersurfaces violating some other version of a Thurston-Benneken bound in high dimensions. So maybe that's hinted that this kind of thing might be expected. And then in terms of fitting into this big picture of at least I suspect that there's an abundance of tight contact structures in high dimensions. This is also supported by this recent paper of Bowden, Hiranella, Moreno, and Zhao, where they construct lots and lots of interesting tight contact structures on high-dimensional spheres, which really contrast low-dimensional case. So again, it's all in agreement with this conjectural picture there being lots of tight contact structures in high dimensions. In terms of like doing what I did today and trying to extend it to some higher dimensions, maybe saying that there's no such, that characteristic numbers, characteristic classes don't impose any restrictions in higher dimensions. Maybe such a thing is possible, but in order to carry out a proof, I'd need some sort of to know that there's some building blocks in higher dimensions. So in this 4-dimensional case, I had this collection of 2 building blocks with the correct signatures and Euler numbers. I need to do something similar in higher dimensions, but I don't have that many examples of these divisor pairs in high dimensions. There's in fact, I'm sure maybe people in the audience, most people here are probably better than me at algebraic geometry, and so they might have some interesting examples. But I only know of one interesting example in dimension 6+1, which is kind of famous from algebraic geometry and studied from the symplectic point of view by Takahiro Oba. And it says I can take a degree 111 divisor in P1 cubed, and I can take a degree 11 divisor in P2 times P2, intersect it with another degree 11 to get another sort of interesting divisor. This gives me a divisor pair such that the divisors themselves are degree 6 del Pezzo surfaces. And I can carry out a computation here saying that the contact homology is non-zero for the associated convex hypersurface. But that's my sort of only computation I have in higher dimensions. Please let me know. And I'm over time. And I just want to say thank you so much for the invitation and for having me. And if you want to hear me talk about something else, I'm going to be in the next Symplectic seminar, and I'm going to talk about something different about contact submanifolds in high dimensions.
Well, thank you. Let's thank Russell for his wonderful talk.